Good afternoon, everyone. I'm Ahmed Saeed, an assistant professor in the Future University in Egypt, Department of Electrical Engineering. I will present our work about design and simulation of the ETL-Free Perovskite silicon tandem solar cell with 33 efficiency. I'm one of the authors, and with me, Dr. Mohamed Mousa, Dr. Mostafa Salah, Dr. Zekry, Dr. Mohamed Abouelatta, Dr. Ahmed Shakir, Dr. Fathy Zekry, and Dr. Roaa Mubarak. So at first, we all know that in the last few years, there has been a great demand on energy, and according to the statistics, the fossil fuels have been the primary source of energy consumed until now. It's expected that in the coming decades, it is estimated that the renewable energy source, especially the solar cells, will be one of the primary sources of energy that will overtake the fossil fuels. And also we know that the market for the photovoltaics is currently dominated by multi-crystalline and monocrystalline silicon solar cells. And most of these cells are a single junction, which is made like what I said, of crystalline silicon, and have a power conversion efficiency about 22 or 25%. Whereas another material, which is a perovskite, have an efficiency of about 26, which is commercial. So now there are many researches show that a promising result of about 30% for the perovskite photovoltaics. Regarding the single junction solar cells, as you can see, it has a limited efficiency based on a limitation of the absorption of the spectrum. As you can see here, only part of the spectrum is absorbed, while the other part of the spectrum is not absorbed. So this is one of the major problems in single junction solar cells. So one solution to this problem is to build or to use more subcells, 2 or more actually. Each of these subcells composed of materials. Each of these materials will absorb part of the wave length of the incident spectrum. So it is expected that the efficiency will be higher. In this work, we are proposing a design and optimization of 2 subcell multi-junction solar cell, which is simulated using SCAPS 1D. The top subcell, as you can see, is composed of copper oxide, perovskite, and a transparent conductive oxide. This subcell is designed without electron transport layer, or ETL, as the transparent conductive layer, the TCO, is a highly doped, which will play the role of the electron transport layer beside its primary role as a transparent layer. And here is the parameters used in composing this cell. You can find this table in details in our work. While the bottom subcell consists of, as you can see, cadmium sulfide, zinc oxide layers with silicon, also absorber layer in the bottom, as you can see. And here is the material properties of the bottom subcell. Regarding the simulation of the proposed top and bottom subcell, as you can see here, two graphs. On the right, the variation of absorber thickness and the corresponding power conversion efficiency and fill factor. But on the right, on the left, you can see the open circuit voltage and short circuit current with the variation of the absorber thickness. All of this simulation are performed for AM 1.5G and at temperature 300 Kelvin. The results show that the short circuit current density and power conversion efficiency and the fill factor will increase with increasing the thickness to about 800 nanometer. Then the result will be saturated. However, increasing the thickness of the perovskite layer will lead to a decreasing of the open circuit voltage, as you can see, the blue graph. One note can be taken into consideration, it should be taken into consideration, is that the implementation of the practical thickness of the absorber layer cannot exceed 1000 nanometer. The designed top ETL-free perovskite solar cell shows an excellent performance with power conversion efficiency of about 35%. In addition, this design is very simple. For the bottom subcell, the silicon bottom subcell design is illustrated, as you can see in figure. The current voltage characteristic of this subcell shows that the power conversion efficiency of about 13.3%, fill factor about 80%, and open circuit voltage of about 0.5, and finally the short circuit current density of about 41 milliampere per square centimeter. So, in designing this multi-junction cell, we used a numerical technique that's based on one of our published paper before, our published work before. This algorithm is composed of two phases that is employed to optimize the thickness with a coarse step of 50 nanometer and a small step of 5 nanometer. So all the junctions performance characteristics are computed based on the resultant thickness at each stage. This algorithm is an improvement of the algorithm we developed before, and this modified algorithm is more efficient as the number of the overall computation decreased, and also it leads to a faster response in determining the thickness of the top subcell absorbers layer for two-terminal multi-junction solar cell. So the simulation of the ETL-free perovskite silicon multi-junction solar cell shows that the power conversion efficiency of about 33% when the perovskite thickness is about 200 nanometers, as you can see in the figure, and the multi-junction cell with AM 1.5 and the filtered AM 1.5 is applied to the bottom subcell. This multi-junction overall cell with the highest efficiency has open circuit voltage of about 1.9 voltage and short circuit current density of about 20 milliampere per square centimeter and fill factor of about 87%, as you can see here. Also, the quantum efficiency of the perovskite and the quantum efficiency of silicon subcell, and also the overall multi-junction cell are all shown in this figure. As you can see, at low wavelengths, the quantum efficiency of multi-junction cell is almost the same as the top subcell, while it is about 100% up to the cutoff wavelengths of about 1,100 nanometer of the bottom subcell. So as a conclusion to our work, the designed tandem cell has a higher power conversion efficiency and it is presented with a practical thickness range. In addition, a multi-junction solar cell using perovskite as a top subcell and silicon as a bottom absorber layer has been presented. Also, we introduced an optimization algorithm to optimize the thickness of the perovskite material. Our results show that the electron transport layer free perovskite is a promising top subcell, and it can be used with the other bottom subcell rather than silicon. The proposed tandem cell has an efficiency which is higher, about 33%. Thank you all. Please, for any question, you can send to any of this email. Thank you so much.